So section 3.5 is about choosing which procedures you'll use for calculating derivatives. It's not new material. It's just a chance to practice all of the different derivatives that you know in combination with other types of derivatives. I want you to think about whether you would like to see more examples or whether you would like to do more examples, because that's what this video is about. If you choose to skip this video, which is totally up to you, then please open up the 3.5 note sheet and try those derivatives there. If you want to see more examples, that's what this video is for. It's for people who like to learn by watching examples. But there are more examples on the note sheet, so try those ones as well. So some things that I want you to watch out for as you're doing derivatives is that function notation is not the same thing as multiplication, and it gets kind of confused sometimes when you see a kind of a chain of chains. Sometimes I see kids accidentally see this as the natural log of x times cosine inverse of x, and that would be if that were a product, but this is not a product. This is a composite. It's the natural log of cosine inverse of x. So if I were going to take this derivative, I would start by taking the derivative of natural log, which would be 1 over, and then I leave the baby alone, and then I multiply times the derivative of cosine inverse, which is -1 over the square root of 1 minus x squared. Some other things to look out for that I notice kids have trouble with sometimes is the exponent notation for both trig and natural log. That exponent notation goes in sort of a strange place, but what this means is that we're going to take, before I take a derivative, I could rewrite this a little bit. We are going to take tangent of 3 minus x squared, and then we would square the answer. So even though this is in a weird spot, I can rewrite it the way that I just wrote it so that you can see that you're going to work from the outside in as you take your chain rule. And you would start with the derivative of squared using power rule, and you would leave tangent alone. And then you're going to take the derivative of tangent, which is secant squared, and you're going to leave 3 minus x squared alone. And then you're going to take the derivative of 3 minus x squared, which would be -2x. Not really much simplifying you can do here, but you can multiply those -2's together, and you can get -4x times tangent of 3 minus x squared times secant squared of 3 minus x squared. Kids often ask as they're looking at these problems, I see that this is a quotient, and I also see that it's a quantity to the second power, so it's a quotient and it's a chain, and what should I do first? And I guess my advice is to take a look at it and say, overall, what is happening with this function is that it is something squared. The something is complicated, and the something involves a quotient. But overall, this function would be something squared. So I would start with the chain rule, and that chain rule will force you to do the quotient rule. This is a different problem than if I had written it like this. If it were this problem, 1 plus sine of x, quantity squared, over 1 minus cosine x, then I would say, oh, overall, that's a division. Within the division, I will do chain rule because I see that when I take the derivative of the numerator, I will be forced to do chain. So as you're making that decision, kind of look at it and say, oh, overall, this is something squared. It's not something divided overall. Okay, so when I take the derivative, I would start with squared, so it would be 2 to the 1 power using the power rule. You obviously don't have to write to the 1 power. I just did to be extra clear. And then I'm going to take the derivative, working my way in, and that's going to force me to do quotient rule. So that'd be 1 minus cosine x. Be careful because these parentheses matter. We want to take that whole quantity times the derivative of the numerator minus high below all over the square of what's below, and away we go. There's a little bit of simplifying that can make this derivative look a little bit prettier. It's not going to be beautiful no matter what I do, but I can write it so that it's 2 times 1 plus sine of x. And then here I can see that I can distribute cosine through the parentheses. And I can distribute sine through these parentheses. And then I have 1 minus cosine of x quantity cubed, because I had 3 of those. And then just with Pythagorean identity, there's a little bit of simplifying that can happen, because I am going to distribute this negative. And I'm going to do a little jotting up here. If I look at negative cosine squared of x and negative sine squared of x, which is what I'll get eventually, that's the same thing as negative 1 times cosine squared of x plus sine squared of x. And because of the Pythagorean identity, this would just be negative 1. So I can rewrite this so that it looks like and that's just because of that Pythagorean identity that I have written up here, with combining the negative cosine x and the negative sine of x. Negative cosine squared and negative sine squared. Another thing to be really careful about is always rewriting things that you can with negative or fractional exponents, so you can apply either the power rule or, in this case, the a to the x rule. If I rewrite this before I take a derivative, I can rewrite it as 8 to the negative x. I could also use quotient rule, but the quotient rule is a little bit more painful. If I take this derivative, I'm going to get 8 to the negative x times natural log of 8, because that's the derivative of a to the x, and then times negative 1 because of the chain rule. I could rewrite my answer also with positive exponents because we like those better. So it looks like this. But I would totally accept that first answer as well. And then another tip is that sometimes you can do some algebraic manipulation that makes your derivatives easier. I know a lot of natural log rules that would make this, before I even take a derivative, I can turn this into a simpler expression. First, I could do the product rule, which turns this into a sum of natural logs, kind of expanding my natural logs. Not the derivative product rule, but the product rule for logs. And then I can also bring my exponents down in front. So I have x times natural log of e plus 3 times natural log of x. And that's the power rule for logs. Now, the function is simplified enough that when I take the derivative, it's a really simple derivative. Oh, it's not quite simplified enough. What is natural log of e? That would be 1. So I'm actually taking the derivative of 1x, which is just 1, plus 3, and the derivative of natural log would be 1 over x, so 3 over x. The derivative was a lot easier to take because I used algebra to simplify the natural log, or to expand the natural log. The derivative, I could take the derivative as it is, but I would have to do the chain rule and the product rule. But for the derivative as I took it, I only had to do power rule and derivative of natural log. One more algebraic manipulation thing we can do is we have the square root here, but if I notice, this is actually the square root of x minus 3 quantity squared. So when I take that square root, I get the absolute value of x minus 3, because if x minus 3 is negative and I square it, it becomes positive, and then I take the square root of it, so the answer would be positive. If x minus 3 is positive already, then squaring it, take the square root, gives me x minus 3. I can rewrite this as a piecewise function. So this would be x minus 3 as long as x is greater than 3. And it would be the opposite of x minus 3 if x is less than 3. And I'm going to put an equal to on one of those. So when I take this derivative, the derivative is really easy once I do all of that algebraic work. The derivative of x minus 3 would be 1. And the derivative of negative x minus 3 would be negative 1. And there's a corner at x equals 3, so there is no derivative at x equals 3. That's why I don't have an equal to bar on either of my inequalities. All right, so this is some advice about how to make your derivatives easier and just using all of the skills you have to do derivatives. There are more examples on the note sheet for today, so please do some more problems and get some practice in. Thank you so much.